Pressure in fluids. We know that pressure is force divided by area, or P equals F over A, and if the force is measured in newtons and the area in square meters, pressure is then in newtons per square meter. And the newton per square meter is also known as the Pascal, and that's its symbol, capital P, little a. This is a very small unit, and in atmospheric pressure we have around 100,000 pascals. So 5 newtons per square metre would be 5 pascals, for example. If the area is given in square centimetres, there are, if this was a square metre, 100 centimetres along this line, 100 centimetres along this line. So there's a row of 100 square centimetres here, and another row below it 100 times. So we have 100 lots of 100 square centimetres, which is 10,000 square centimetres in 1 square metre. If we go on to square millimetres, we then have 1,000 millimetres along this top row, and we've got 1,000 rows of 1,000 millimetres, which gives us 1,000 times 1,000, or 1,000,000 square millimetres in a square metre. Here we've got a block with a weight of 500 newtons. Note we're given its weight, we're not given its mass, so we don't need to calculate its weight. Okay, if that face is 5 metres, that 1 metre and that 2 metres, the way it's lying at the moment, the pressure is force divided by area, its weight 500 newtons, the area in contact with the ground is 5 times 2, giving a pressure of 50 pascals. If we put it on its end like this, we then have an area of 1 times 5 metres, which has doubled the pressure. And if we stand it on end like this, we now have just 2 square metres, so we've now got 250 pascals. So this way round, it is exerting 5 times the pressure on the ground as it is if it's lying on its flat face. Fluids. What do we mean by a fluid? Well, a fluid is a substance that can flow, so liquids and gases. Here we've got a pipe and it contains a fluid, and if this at this side is pressure A and here we've got pressure B, if pressure A is greater than pressure B, the fluid will then flow to the right, like this. Here we've got a syringe. If we exert force F on the plunger of the syringe here, and the piston has an area A, we're going to get a pressure in the fluid given by force divided by area. Here we've got a special syringe which has got a spherical bowl with lots of little holes in it, and I fill this blue to signify water, and if we then push the plunger down quickly, we get the water coming out something like this, out in all directions. And that basically shows us that in a fluid the pressure acts equally in all directions, as long as the depth is constant. We'll look later in a different video as to how depth affects pressure in a fluid. Okay, this can be used in things called hydraulics. What we've got here is a force 1 acting on a small piston of area 1. That will then produce a pressure here given by force 1 over area 1. But we've just seen that the pressure in a fluid is the same in all directions. Now I know here it is going slightly deeper, but this is a small depth change. We don't need to worry too much about this. So we'd have the same pressure here. We'd have the same pressure here. Then that is going to exert a force on this piston of area 2, and that will be force 2. And so from this side, the input, we have that the pressure in the fluid is force 1 divided by area 1, and that is the same as the pressure here. The pressure all the way around here is the same, because this depth change is negligible. We can ignore it. Okay, so the pressure is also force 2 over area 2. We can rearrange this to find out what the output force, force 2, would be, and that's given by this expression. So if area 2 on the top here is bigger than area 1, as it is in this diagram, we have a large output piston and a small input piston, it means that the output force will be bigger than the input force. So a hydraulic system, rather like a lever, can act as a force multiplier. We put in a small force, we get out a larger force. If the diameter increases by a factor of 4, the area will increase by a factor of 16. because the area is pi r squared and 4 squared is 16. So if we increase the diameter and therefore the radius by a factor of 4, we increase the area by a factor of 16. Therefore the output force will be 16 times the input force. However, it's not a win-win situation. If the input piston was pushed down a certain distance, the output piston would move up 1/16 of that distance. As the force increases, the distance reduces by the same factor. The input work done, assuming the system is 100% efficient, will be equal to the output work done. So the input work done, if we're using the hydraulics as a force multiplier, would be a small force through a large distance, giving us a large force through a smaller distance. An example of that would be a hydraulic car jack. What we've got here is a simple diagram of a hydraulic car jack. This is the handle, which is pivoted at this point and attached to the input piston at this point. You'll see that the handle is also acting as a force multiplier, as the effort, which we'd put in here where we put our hand, is much further from the pivot here than the load is, which is this point. The car would go at this point here, so this is our large piston, which would go up. The small input piston here only requires a relatively small force, but has to be moved through a large distance. So if we move this piston down maybe 2 centimeters, this piston might only move up 0.5 centimeter. That produces a large force to lift the car, but it would move through a much smaller distance. In reality, there's also an oil reservoir in here. This is an oil that passes through from the small piston to the large piston, and so what the mechanic would have to do is push the handle down to raise the car a little bit. As if they raise the handle back up again, this would again fill up with oil, and they could pump the handle several times to raise the car a few centimeters for them to work on it. This system is also used on equipment such as diggers and cranes, so a relatively small low power pump can produce very large forces needed for diggers and cranes.